Yep. Yeah, just to not bore everyone who knows this very well too much, it's going to be a bit faster. So I mentioned that this here is a quadratic in Q. So let's call this star, and it's quadratic in these QE. And we want to complete the square in QE, and it's this YE. And this is a bit of a annoying exercise to complete the square. Yeah, but you're of course invited to do it as an exercise to work this out by yourself, but I can give you the answer that it's convenient to define something that is mathematically also very interesting, a certain v minus 1 times v minus 1 matrix, which is called the graph Laplacian. So this is a matrix indexed by the vertices minus this one excluded vertex, and it's a symmetric matrix. And it's defined as the sum of all edges. And we take kind of this epsilon matrix, this incidence matrix, and wedge in between these Schwinger parameters. So this is actually pretty simple matrix. This is for UV in this reduced set of vertices. And yeah, it has very nice mathematical properties, and it kind of mimics the Laplacian operator on a graph, on a weighted graph, where each edge has length xe. So
I'm sorry, can I ask a question?
sure.
I'm over here.
Yeah.
So my question is the eta parameters that are the exponents of the propagators.
Right.
From the point of view of the integral parameterization, don't have to be integers, do they?
No, eventually they don't have to be integers, especially, yeah, also not in the beginning, right? Right. They
But
can also be.
is it ever interesting to consider a sort of analytic continuation on those parameters?
I mean, so in three-dimensional space, it's very interesting to have them be half integers, for instance. So
Okay.
often you're interested actually in non-integer values for them.
Okay. And just a small comment. It's a little bit hard to see the board, like the writing. Could you write bigger?
Too small, or
Yeah, I think it's just like the lighting is not. Yeah.
lighting, or too small? Both. Okay.
Yeah.
I'm sorry. Sorry. Okay, I'm trying my best to write bigger, but please tell me. Okay. So with this definition, one has like a nice, we can complete the square, and I'm just going to write this down quickly. So we have some QE, and we shift them somehow, and I call these shifted versions of the QE Q tilde, because we are eventually integrating over the QE. We are not really interested in any dependence on these shifts, so it doesn't really matter how we shifted them. Then we have bigger, one of the, when we have this Laplacian here appearing with the y's, and we have the Laplacian also appearing with the external momenta. And actually, we need the inverse of the Laplacian for that. And then we only have the mass terms. The matrix Laplacian?
Sorry. Is that LUV?
Yes.
A Laplacian that is like a matrix instead of a scalar?
This is a matrix, right? Or what do you, sorry,
Yes, but is it like the Laplacian that we use in QFT? That's all I'm asking.
This is the graph Laplacian, so it's not like the
Okay, thank
Laplacian
you.
operator, which is a squared differential operator, but it's kind of a combinatorial counterpart for this Laplacian operator. So also you mean this kind of Laplacian, the delta Laplacian? Yeah, so this is the Laplacian on like R on the real line. And there's like a Laplacian, of course, also on R2. And you know that you can also write down a Laplacian on the sphere, for instance. And this is a Laplacian here for a discrete object, for a graph, where we are not continuous, but we only have like a discrete number of points, and they are connected. And the distance between the different, so the length of each edge is encoded by these xe's. So it's a bit of a cartoon version of an actual Laplacian, but it's named a Laplacian for a reason, because it's really this discrete counterpart of this usual Laplacian. It's a graph Laplacian. And then there's the epsilon up here. Okay, so this shows us that we can just rewrite this exponential here as something that is quadratic in these q's. So the q tilde is just a shift of the original q's and the y's. And then we have something that does not really depend on the q's and the y's. And so we can just perform these Gaussian integrals over y and q. It's not really a Gaussian integral, it's like a imaginary Gaussian integral. So what we have to do is we have to use such a formula where we integrate over kind of an imaginary, let's do it like this, imaginary version of the usual Gaussian. And this is going to be something like minus I pi over 4 times square root of pi, I believe. And the only thing that we need to be careful about is here the signature of space-time, because the signature is going to influence the signs of the quadratic terms. And this is why we get like different phases depending on the space-time dimensions. This is just a technicality. Anyway, if we are just evaluating this, we get the parametric representation, the first one. So when we are evaluating this, it's helpful to also define u of x, which is product of all edges times the determinant of this Laplacian, this graph Laplacian f. This is the term that comes from the integration of all these q's and of these y's. So the determinant of L comes from, actually up there. So if we integrate over all these q's, we get a product over xe's in the Gaussian integrals. And if we integrate over the y's, we get the determinant of the L as a term in the result. So we need this u of x as a prefactor. And so we find that ig is e minus I pi d minus 2 times L. So this is the d minus 2 comes from the signature of space-time, which is Minkowski. So we have d minus 1 space-like and 1 time-like. So this is the combination that pops up. And as a normalization factor, we also have these gamma functions that we carry around. And then we have our integrals over these Schwinger parameters, where we are integrating over one Schwinger parameter for each edge. And the actual integral involves now this u, which comes from the Gaussian term. And then we have these leftover terms up there that don't depend on the y or the q. And we can write them, so they are written compactly by IV plus sum over all E xe times epsilon. So this is, and V is just minus PU times PV, and this contracted with the inverse of this graph Laplacian plus the edges with the masses squared. So this is the parametric representation, and this is already much more convenient because here we now have our d, our space-time dimension, as a free real parameter, and we also reduce the dimension of the integral by quite a lot. We now have an e-dimensional integral, and before we had an L times e-dimensional integral and L times d-dimensional integral, and this is already much more convenient. What's a bit annoying is this oscillating integral here, and the next step is also to get rid of this. Yeah, so we are still not at a compact integral because, of course, this positive r to the power of e is not bounded. So we still integrate to infinity, and we are not over a compact domain. So can kind of, oops. Fix this for now. But the problem is it's non-compact. Plus it's also oscillating. And this motivates this algebraic representation over a compact domain, and I like to write this down over projective space. And projective space is fantastic. It's fantastically convenient to deal with these kind of integrals. And I'm going to sort of give a bit of an introduction into integrals of a projective space if you're not familiar with that. We can do this on one of these sideboards. So what is projective space? So it's written as, say, R P n minus 1, and I'm always using n minus 1 because I want to keep the number of variables equal to n. So this is the space of all tuples. Larger. x1 to xn. We can think of them as like boring vectors in Rn. But we want to have like two such tuples equivalent if they can be translated into each other by a scaling. So we want to mod out a relation. And the relation is just that if we multiply each parameter with lambda, then we are supposed to think of this as the same point in projective space. And the lambda, the scaling, of course, has to be non-zero. And a way to think about projective space, a very useful one, is to just think about it as the space of all lines that go through the origin. So, for instance, you can make a little picture of in two-dimensional space. So this is x1, x2, and a picture of RP1 is now the space of all lines that somehow go through the origin. So these are, each line is some element of RP1. And we now want to restrict this still a bit. We want to make a, we want to fix like a positive part of this projective space. And so what I do is I define the positive part of projective space to be the space where all the homogeneous coordinates are positive. So if you want, you can think about this as a kind of a gauge symmetry. We can just rescale all the vectors that we have, and we are supposed to think of this as the same element. And the elements of Rpn or Rpn minus 1, they also traditionally denoted with this square brackets. So x1 to xn just means that, so this is an element of Rpn minus 1. And it just means that we are going to think of this tuple here of these x's as being invariant under rescalings or under overall rescalings of these x parameters. And now we define a subset of this projective space. Rpn minus 1 plus. And this is just the set of all these points in Rp n minus 1, where each of these coordinates here is positive. So as a picture, what we have here now is like the space of all lines, but the lines have to end in the third orthant, have to start in the third orthant or end, doesn't really matter, and in the first orthant, and the higher dimensional analog of this. And the lines are also not allowed to touch the coordinate lines. Yes? The question is if this is a coordinate chart.
Yeah, this particular tuple that you have written is that a coordinate chart for this space? Because I thought maybe the appropriate thing to do would be to fix one of them to unity.
Yeah, you could do that, yeah. Yeah.
Okay.
But this is not, so I'm not talking about a coordinate chart here now. This is just a subset. So this is smaller than Rp n minus 1. So this is only the, so here with the whole Rp, we have like all lines that go through the origin. And here in Rp plus, we only have those that don't touch these kind of negative zones that we excluded. So we want them to be either completely positive, so here all coordinates are positive, or all coordinates are negative. So this isolates a specific subset of Rp plus, of projective space. But what we can do is we can actually use this definition to write a chart for Re larger than 0 for this positive tuples. Are there more questions? So there's a diffeomorphism from Rp plus E minus 1. So these are in homogeneous coordinates, we have here x, e. So we are not really caring about the scale, overall scale of these parameters. We can also add primes to this. So let's say these are just coordinates of Rp plus with e variables. And then we want to take the product with like one copy of R larger than 0 and call this lambda. So this whole product, this is tuples of one element of this positive projective space and a lambda, positive lambda. And we want to map this to our Schwinger parameters in this space up here. And we do this by just saying that our original parameters are going to be equal to lambda times xe prime over the sum over all the xe primes. So this is a good expression in projective space because it's projectively invariant. So both the numerator and the denominator are scale invariant. So we can use these as functions over our projective space. And this is a nice parametrization of our positive orthant here that we did here. And yeah, we can, so this is a diffeomorphism. So yeah. And we can use it to just change coordinates in this kind of integral here. To carry around this thing. So if we hit, if we use this diffeomorphism to transform this integral, what we get is the following. Yeah, if you have, maybe let's skip this step. What we get is some kind of prefactor that's not so interesting, and we end up with an integral over RP e minus 1 plus, and we again have here these Schwinger parameter powers. We again have u d over 2, and then we additionally get a I minus v plus e. And I skipped one step now, because it's a bit boring. And this omega form, this omega here is the pullback of this flat kind of volume form on this positive orthant, and it's written as the alternating sum over all the d logs of these new variables. And what is missing is this integral over lambda, which I now skipped, and this integral is just this is just another gamma function that pops up in between. So this is, let me write it like this. So a step in the proof is to evaluate this integral over this overall scale. And this looks like this. Where we scale everything via this lambda. So this is like an intermediate step here that I skipped in this upstairs expression. So this is where this this term, like this rational function involving this v, comes from. And it's this residual integral over this remaining like overall scale that we also need. And we can evaluate this integral, and I did it implicitly there by just evaluating it to a gamma function times this minus v plus I epsilon to the omega term. And this again only works because we have the right sign here in terms of the I epsilon. And it would also work in Euclidean space. So this is now the nice projective version of the parametric representation up there. And mathematicians really love projective space. The reason is, yeah, first of all, projective space is compact. So there's no issues with some points at infinity. So there's only a nice compact set of lines through the origin in each dimension. But also projective space has lots of very nice magic properties. So it's a bit, I don't know, sometimes in mathematics you get more, you feel like you get more than you paid for. It's like this, for instance, with holomorphic functions. If you're only used to like functions in one variable in real space, then you know, like everything is differentiable and so on. So you kind of don't expect that much from the differential functions in the complex plane, but you get much more than you kind of expect naively. And it's a bit similar with projective space, maybe not quite so strong, but projective space is still so much better than affine space. So you can do much more cool stuff there. So yeah. So I mean, maybe for practical purposes, illustrate like some integrals in projective space. Maybe you haven't been exposed to them.
Excuse me, I have a question.
Much.
In this sort of D-log volume form, just to make sure, is the hat saying omit this term from the wedge?
Oh yeah, sorry, I didn't really say that, but yes.
Okay, thank you.
So we have E minus, so this is an E minus 1 degree form. And this is correct because this projective space is also E minus 1 dimensional. Yes, good question. Thank you. Any more questions? Why projective integrals? Here's one example. So you might know. So if you ever computed a Feynman integral before, you know this integral. The beta function. If you don't know it, then it's also not so bad. So typically it's defined as this integral from 0 to 1. And it turns out to have like an explicit expression in terms of gamma functions, but that's not so important for now. And it's like a nice example. It's the Feynman integral that is associated to this one is this massless bubble integral, which also appears a lot. But you can just write it as a projective integral by using the diffeomorphism where you just send the interval to this positive projective space. And we embed this interval just in here. So these are the coordinates with 1 and 1. And we say that we want to embed. So we have this interval, and we just take the line which cuts this interval as our representative. So we can also do this explicitly. So this gives a nice diffeomorphism from this interval. Actually, we have to take the closed interval, but as we are the open interval, sorry, but as we are integrating, it doesn't really matter. So this maps into RP1 plus, and the map is just t goes to the coordinates of t and times 1 minus t. And if we do this, if we just work this out, and it's actually not so hard, so I invite you to do this as a nice little fun differential geometry exercise. So if you like differential geometry, then we get an integral over this positive projective space, and we integrate over both these coordinates, and these just become the news, these new powers, and down here we integrate over x1 plus x2, and the power is nu 1 plus nu 2. In the differential form, it becomes dx over x1 minus dx2 over x2. And this is also this canonical form that we had before for the specific integral. And you see, for instance, here you have like a nice symmetric representation of this integral, where you can maybe a bit better see that this thing here is going to be symmetric in nu1 and nu2. And in a way, this is also the theme that one discovers, that in this projective space representation, you just have a more symmetric representation of these integrals. And usually the symmetry is broken once you go to an affine chart. So in a way, this encodes like many integrals to the price of one. As an illustration, we can just pick another diffeomorphism of this projective space. So let's pick this diffeomorphisms where we just embed like the positive real numbers as this line here. So we can add actually some color. So just pick the projective line, the point in projective space that corresponds to the intersection point between this red line and the respective line for the origin. And if we do this, we get an identity. So we can write this then again as an integral from 0 to infinity. 0 to infinity is now this red line. And it's, if you have some training with this, practice a bit, you can really write this down immediately, that this is an integral over this coordinate of this line. So this is parameterized then by t, and we have here integral over with measure dt over t. So with this kind of stuff, we are ready to tackle our Feynman integrals now with like really cool algebraic tools, because up to this whole I epsilon business, the integrals are completely algebraic. As kind of due diligence, I also want to explain to you now how complicated these integrals become, depending on the kinematic structure. So this is now about the particular structure of these integrals. So both the numerical and the conceptual complexity of these integrals crucially depends on this v term there, together with this I epsilon. And I'm not going to give so much detail on the more complicated cases. I'm mainly going to talk about the very simple cases. Yep.
I guess the whole point of writing Projective space was that the integrand doesn't have any singularity that the boundaries, right? The integration region becomes compact. I can see that, but can you see how like the boundary of the integration region doesn't really affect the analytic structure of the integrand?
So the question is if the boundary of the integration region does not really affect the analytic structure of the integrand. I don't know. So I mean, one thing here is that this canonical form, it has poles on the boundary. So if we don't have something here that cancels these kind of poles, then we have a divergence. But I'm going to talk about more about this probably tomorrow, about these kind of divergence issues, how to deal with them. But the divergence issue here is now encoded mainly in the boundary, if this is what you're alluding to. And studying the boundary really tells us about the divergence or the convergence of these integrals. Does this answer the question?
We can talk more about it after.
Okay. Good. Any more questions? We started a bit late. How much time do I actually still have? Okay. Yeah, so I just wanted to mention that we are now talking, or we now have this representation, and I still want to add like some interpretation of the complexity of these integrals. So the crucial term is this v term, and so complexity of Feynman integrals, and the v term is given by minus p dot minus pu dot pv. So this is again one incoming momentum for each vertex of our graph. And we contract this with the inverse of the Laplacian. And we add the masses square times our Schwinger parameters. And you can see that we can also interpret this thing here as a trace of some matrix, say P, times the inverse of this Laplace matrix. And this P matrix, so P is really just the Kram matrix that comes from these external momenta. And the complexity of this integral crucially depends on the structure of this Gram matrix, on these external kinematics, together with these masses. So there's one very easy regime or region. So if this matrix P is negative, I'll do that larger, negative semi definite. So negative semi-definite means that all its eigenvalues are negative or 0. And in that case, because this L matrix, this Laplacian, is a positive semi-definite matrix, you can see that this trace is always going to be negative. And it cancels this minus sign here. And with the masses, we are always getting something which is exclusively positive. So in this case, V has a definite sign. But there's something extra to this, namely that we can find a change of coordinates for these p's here that transforms our Feynman integral problem into an entirely Euclidean problem. So we can really kind of do something like a Wick rotation, but not quite like a Wick rotation, because we can end up with completely different momentum vectors by this operation. But still, the Feynman integral problem as it stands is equivalent to some Euclidean Feynman integral problem. So here we are in the Euclidean regime. And additionally to this definite sign, this Euclidean regime also allows us to do like some simplifications to the problem, or actually only in this Euclidean regime, many of the aspects, especially of the convergence of these kind of integrals, of the Feynman integrals, is completely understood. And there we can do a lot. And because of the finiteness of the Feynman integrals, we even have fast integration algorithms for them. So we can evaluate the Feynman integrals relatively fast. So everything is kind of quite well understood in this case. And this is also going to be the main topic of tomorrow's lecture. But I want to mention also the other cases. So the interesting thing is that there's an intermediate zone. So you might expect that it's negative semi-definite, and otherwise we just have like maybe positive definite or indefiniteness, but still we can like see sign changes in this V. But there's actually something else. So there's something which one can call the pseudo-Euclidean regime. And it's kind of interesting that this exists. And you can characterize it as follows. You want to require that for every subset of the vertices, V prime of V. So this is just a subset of the vertices. I realize I have too many V's. Let's call this V of X here. So this is this function that depends on Laplacian. And this is now vertices, these V's. So maybe I should just add like some, this is vertex, this has a little head. And the rule is that if we sum over all the entries now of such a subset in this V head subset space set, and we take something which is a very weird matrix operation, but we just sum over all the entries of a specific minor of the matrix. So we just sum over all the entries. And if we do this, and if it's smaller than 0, so negative for all these subsets, then so this is an if. So if for every subset we have this property that this P matrix is negative if we sum over these subsets, then the V of X function is always larger or equal to 0. And we have a definite sign for the V of X function. Unfortunately, however, in this pseudo-Euclidean regime, we cannot really use the nice algorithms to check for the finiteness of the Feynman integral that we have to our disposal in the Euclidean case. Yes?
Do we also impose this condition for one element subsets? In particular, that the diagonals would have to be negative?
Yes.
Yes.
The diagonals have to be, yes, they have to be all, yeah, negative or 0, right?
Okay. Does this have a physical interpretation?
That means that we cannot have massive on-shell legs.
Okay, thanks.
So this is also very restrictive. But it happens actually a lot. And then, I mean, there's a kind of a, so then there's a regime which is outside of this property. So if P does not fulfill 1 or 2, then we are in the Minkowski regime. So there, this V can actually change signs, and this is yeah, this can get very complicated, and there the so-called Landau singularities also appear of these integrals, and yeah, there's lots of research ongoing on these kind of singularities. Just a brief reminder of what the problem then actually is. So why do we actually bother about the definiteness of this V? So the problem comes from, so effectively what we end up with is integration problems where we are faced with some integral, say for instance from -1 to 1, and what we are integrating is, so we want to integrate through some pole of our integral. In general, we have some rational function. So this v is going to be a rational function, but rational functions can have poles, and we want to integrate through this pole. And then the I epsilon tells us that we are supposed to integrate around this pole in a specific way. And in this particular example, we can do it, and we get something which is imaginary, but which is somehow well-defined and definite. We cannot do it. We're just kind of hopelessly lost if we are required to do this at the end of our integration domain. And if we are in this kind of situation, then we just get essentially infinity. And also if we are in a situation where we are integrating over something which is squared. So if we don't have a single pole but a quadratic pole, and we want to do these kind of tricks, then we also get actually nonsense. So cannot really do that. So this is the only case where this I epsilon is actually useful. And but there can also be other problems like the squared issue, and these square issues are usually these Landau singularities. They can also appear here as these endpoint singularities. So these are these different kinematic regimes. And tomorrow we are only talking about the Euclidean regime. And there we can actually do quite a lot, fully combinatorially. And it's like an open problem to extend everything to these more complicated regimes. And the reason for this complexity really comes from these Landau singularities or endpoint singularities. There's still some extra regime issues. So sometimes people also talk about generic or exceptional kinematics. The problem is that so the interesting cases are never generic. So it's not so interesting actually to think about these generic cases. So there's a complementary classification, meaning like generic kinematics. That means that these PUV expressions, that there's like no subset so no V prime hat such, this is too small, sorry about that. So there's no V prime subset of the vertices such that if we sum over these if we take these minor sums, then this is equal to like some edge squared. So this ensures that there cannot be a non-trivial cancellation between the mass term and the, oh, I erased it in this. So in this definition of this V function. And in this generic case, we can also do like a lot and actually learn a lot from the Euclidean case, especially in this finite, especially for the finiteness. But the exceptional cases where we have these kind of cancellations are also not so well understood. And this is also very important because once we have on-shell kinematics, like someone asked, so whenever we have some particle on-shell externally that is equal to some mass in the inside, or if you have like something which is massless, and we also have a massless leg, then this condition is immediately violated and we are in an exceptional configuration. So 2 prime, otherwise exceptional kinematics. Okay, I think it's a good place to stop.
All right, we have time for a couple of questions before the buses arrive.
I was just wondering, if the graph Laplacian is singular and non-invertible, then obviously there's a bunch of steps that don't go through. Is there an intuition for what graph looks like that? What has a 0 eigenvalue?
So the graph Laplacian is always non-zero if all the Schwinger parameters are positive. So you have to take some of the Schwinger parameters to 0 to make it singular. So, but these are also the interesting singularities. So the finiteness of these integrals, so the u can vanish on the boundary of the integration domain. And this exactly happens when the Laplacian becomes singular. And yeah, so studying this actually leads to the finiteness proofs of these Feynman integrals, and also leads to evaluation algorithms. You can also use this to evaluate the integrals numerically.
So if we only have massless particles running inside the graph, do these integrals become much easier to do? It doesn't look like, right? Because then the x
No.
dependence drops out of v, right?
Um,
Because v is like sum of the mass squareds times x. So you have no x dependence in the v. And then
no, the V is, so I erased it, but the V is just minus trace of this P matrix inverse, Laplacian inverse, plus me square xe. So if you are massless, if you put yourself, if all the internal edges are massless, then you just lose this term, but this term remains.
that has x's in it?
That has, the L has x's in it.
Ah, okay. Okay.
The L is up there. It has 1 over x.
Oh, I see it. All right.
Yeah.
Thank you.
So that's very important, the x is in there.
Michi?
Yep.
So I'm thinking of the capital B integral with nu1 and nu2 that you showed, and x1 and x2. And I'm trying to identify capital omega, because
Yes.
you have only x1 and x2, and I do not see how you get a little x sub e that you omit there. Is it that you have 3 parameters there?
No, so this is, so the omega for the beta is like the alternating sum I is in 1, 2. And yeah, so it's the wrong sign, but if we just agree that we want to do yeah, so this is, of course, I mean, we are just having a bit trouble here maybe with the smallness of the number 2. But yeah, this is just x1. So, or let's just do it like this. So this is just -1 times dx1 over x1 plus, so here we omit dx2, x2, so this is omitted. And then we take plus with dx1, x1, omit this, wedge dx2 over x2. So this is just minus dx1 over x1 minus dx2 x2. So maybe there's a sign issue. But I actually think the other sign is correct, but it doesn't really matter that much. Yeah. So you always have to think about orientations of these kind of spaces, and the signs, they get mixed up in the wedge notation.
No, yeah, the only thing I was missing was the summation at the very beginning. Thank you very much.
All right, if there are no more questions, let's clap once more.